To talk about similitude again. This time we're going to move on to what's called incomplete similarity, and it's something that comes up quite often when we're dealing with dimensional analysis problems. One of the classical numbers that we end up having to deal with incomplete similarity is the Froude number. The Froude number is important for flows with free surface effects. So say you have flow going around a boat, you have water flowing in, say, a canal or in a channel, or flow going over waterfalls. One example that you may have experienced in sort of your life is this example of a hydraulic jump that's related to the water, say, going down a gutter during a rainstorm, and you'll see the water level rise as it's actually going downhill and flowing as it would, as you can see here on the bottom right-hand side. So you have a flow that's kind of moving from left to right, and you have a surface that appears to rise. Usually there's some strong turbulence in there associated with that dissipates energy. And this rise, as you're going downstream, is very counterintuitive, because we think of, if we have a head, that the flow should be going back in this other direction. And this is related to the flow speed actually being greater than the wave speed. And that's one of the ways we can actually think of the Froude number. It can be thought of as two different things. One, the ratio of the flow speed to the wave speed. And we can write it like this, as the velocity divided by the square root of GL, where GL is the wave speed. This kind of is more of an interpretation that's like a Mach number, where we have the velocity divided by the speed of sound, where the speed of sound is a wave speed. Also, the way we talked about it the other day, the ratio of inertia forces to gravitational forces. This is another way to write it, and you'll see it sometimes. And as I said, in such cases, we can also think about drag. So here on the left-hand side, sometimes when we think about the type of drag that you'll have on a boat moving through the water, there's certainly frictional drag, and that frictional drag is going to be associated with shear stresses on the bottom of the boat, but also the waves themselves. The waves act to generate an additional drag force that needs to be accounted for. So what is incomplete similarity? It's also sometimes called distorted models. Sometimes you'll see that terminology. It's if we have one or more similarity requirements that cannot be met. And one of the examples is if we're trying to match both the Reynolds number and the Froude number, which would come out from our dimensional analysis, but maybe we can't. And so I want to do an example that will kind of cover this. So imagine we have a boat that's moving through the water, and we want to look at trying to match different non-dimensional numbers. In particular, we want to be able to match both the Froude number and the Reynolds number. So this is, as I said, an example of incomplete similarity, and this is when we can't match all, now let's say it this way, when we can't match one or more dimensionless parameters. So you have all your pi groups, and it turns out that maybe you can't match one of those. This is what this means. And as I said, the classical example is when we try to match the Froude number and the Reynolds number. So for a boat, so say we have a boat that is, I don't know, with a little smokestack here that's moving in the water, and we have it's moving, say, at some velocity, characteristic velocity v. And we have some length scale of the boat L, and of course, the gravity is acting, and we have these waves that are acting and pushing against the boat. You can kind of maybe think of it in a way, if we look at the boat from a plan view, maybe the boat looks something like this, and then you have these bow waves that come off, and these waves are acting against the motion of the boat. And these waves are leading to what we're going to call wave drag. So it's a relatively important phenomena. And so, as I said before, you're going to have wave drag, and then we'll also have skin friction. So those are the two types of, so the total drag is going to be the wave drag plus the skin friction. And we're going to focus on the parameter that is dependent, that the wave drag is dependent on, which is the Froude number. So the Froude number, as we talked about before, is related to the speed of the water to the wave speed. So the Froude number is V divided by the square root of GL. So in one of these similitude problems, what we're trying to do is match the model and the prototype. So what we would do if we follow the procedure from last class, so I say, okay, I've got the Froude number of the model and I need to match that to the Froude number of the prototype. So how do I do that? Well, I'll have the velocity of the model divided by the square root of g in the model times the length scale in the model, and that's going to be equal to the velocity of the prototype divided by gravity for the prototype and the length scale for the model. Now, generally, gravity, we can't vary it too easily, so if the gravity in the model is equal to the gravity in the prototype, then that kind of limits what we're able to do. So if we have the ratio of the model to the prototype's velocities, then this is going to simply be the ratio of gravity of square root of gravity of the model over gravity of the prototype times the square root of the model length scale divided by the prototype length scale. And I apologize, I put an M over there, and that should be a P. Well, these are equal to one another, so that's going to be 1, and we're just left with the velocity of the ratio, the velocity of the model to the velocity of prototype is equal to the square root of the length scale of the model to the length scale of the prototype. Okay, that's not a problem. However, we must also match the Reynolds number to have complete similarity. This is our dynamic similarity parameter. And so what happens if we do that? So we'll have matching the Reynolds number of the model to the Reynolds number of the prototype, which will look like U of the model times D, let's be consistent, length scale of the model divided by the viscosity of the model. And again, this is the kinematic viscosity, equal to mu over rho, equal to the velocity of the prototype times the length scale of the prototype divided by the kinematic viscosity of the prototype. If we look at, and let's make, again, for consistency's sake, let's keep those V's because they're the same thing. And if we look at the ratio again, the velocity of the model to the velocity of prototype, it's a velocity ratio that we found was the square root of the length scale of the model to the length scale of the prototype. What we get for the Reynolds number is that we have the viscosity of the model divided by the viscosity of the prototype times the length scale of the prototype divided by the length scale of the model. Okay, well, based on what we had up here, so this guy up here, I need to bring this down to here because they should be equal to each other. So that says that we would have, this should be equal to the square root of the length scale of the model divided by the length scale of the prototype. And like this. Okay? And so now we're going to go ahead and substitute that in. So we have length scale of the model divided by length scale of the prototype. Okay. So then from this, we can see that the ratio of the viscosities now should be equal to Lm times the square root of Lm divided by Lp times the square root of Lp. So we're just multiplying these guys like this. And as we do to solve for nu m over nu p. And this can be simplified just a bit more so that we have the ratio of the viscosities. I can bring this in by squaring it. So I'm going to have the square root of Lm cubed divided by Lp cubed. And so that's just because in order to put that under the square root, I need to square it. So if I take the square root of it, it comes out, it's the LP. And then this tells me that the viscosity in the model that I'm going to have to use would be equal to the viscosity of the prototype times Lm over LP to the 3/2. All right, so what does that mean? This is the viscosity that I need to use in the model. So most real world problems will have the viscosity for this kind of thing would be equal to the viscosity of water. And so that means that the viscosity is going to be about 1 times 10 to the negative 6th meters squared per second. And say maybe, for example, that let's say we have a 1/10 scale model. So we're going to put a 1/10 scale model of a boat into our water flume, and we want to run this same experiment. So if we have a 1/10 scale model, again, that means that the model is equal to the length scale of the prototype divided by 10, or LP is equal to 10 Lm. And we can now go ahead and substitute this into our equation that we have here for the kinematic viscosity. So the kinematic viscosity of the model is going to be equal to the viscosity of the prototype, or water, and then we can substitute in, we have Lm, and then we're going to divide that by LP, and LP is equal to 10 Lm, so 10 Lm to the 3/2. And so so this ends up being 0.1 times the kinematic viscosity, 0.1 to the 3/2 times the kinematic viscosity. So what do we have for that? We'll have 1 times 10 to the negative 6 meters squared per second. That came from over here. That is the kinematic viscosity of water times 0.1 to the 3/2. And if we work that out, we end up with 3 times 10 to the negative 8th meters squared per second. So that's our viscosity that we need in the model. So viscosity in the model in order to match Froude number and Reynolds number. So let's write that down to be clear. So this is the viscosity required to match the Froude number and Reynolds number between the model and the prototype. Well, is that a problem? Well, it turns out it's actually quite a big problem. As we saw, the viscosity of water is about 1 times 10 to the negative 6th, and so 10 to the negative 8th is 2 orders of magnitude smaller. And it turns out it's very difficult for us to find materials, liquids that have these kind of low viscosities. For example, the viscosity of mercury is about 1 times 10 to the negative 7th meters squared per second. And so this is sort of a very small kinematic viscosity. So as a result, we can't match the two. So this ends up, so therefore we can't match viscosities. And as a result, we have to make a decision. So what's our decision? The decision that we typically make in this problem is that we match Froude numbers. And the reason that we match Froude numbers for this problem is research and experience show that the Froude number dominates over the Reynolds number in these processes. And you would try to have your Reynolds number be as close as possible to the Reynolds number that you would have that you would ideally have. However, the first thing that we try to match is the Froude number, and this is not uncommon. Another thing that we might often do is if we can't match the Reynolds number and the Froude number, maybe there's a time period where it doesn't matter. Say, for example, if we look at our figure of the drag coefficient as a function of the Reynolds number, say for a cylinder. This is flow around a cylinder. flow around a cylinder, it kind of has this sort of behavior. We'll talk more about what it means, but if you think about this region right here, the drag coefficient is not really a function of the Reynolds number. It's almost constant. And in that case, if you are looking at a situation where the model is not a function of the Reynolds number, then we may not have to worry about the Reynolds number. We could say that even though, say for example, say our model Reynolds number is down here, say that's the Reynolds number of the model, and the prototype Reynolds number is way up here, the drag coefficient isn't really a function of the Reynolds number. So maybe we don't have to match it there. So there are times that with incomplete similarity that we don't have to worry too much about it because maybe it doesn't matter too much. And oftentimes that's the case. If we have a situation where the drag, say for example, is not dependent on the Reynolds number for some small region. And sometimes we can actually extrapolate as well. There are dangers with that. Sometimes we extrapolate because you have to assume that whatever the behavior is at some point in your say drag coefficient versus Reynolds number, if you know you're in this regime, then no problem. But what if you don't know what the shape of that curve is a priori ahead of time? And so maybe you're really kind of doing the first test here, that's the model, and your prototype is really down here, then you'd have maybe a really big difference, especially since these are log scales. So that's the big piece that I wanted to talk about for incomplete similarity. I would say go back to the PowerPoint, and you'll see that I've added another example. This is not necessarily an incomplete similarity problem, but it's another worked out similitude problem that you can practice on for getting ready for quizzes and exams. Remember, similitude and dimensional analysis will not be on the midterm exam.